Hey everybody. So today's video is going to be about paradoxes and statistics. I sort of feel like, especially among mathematicians, that people treat statisticians like the work they do is a bit more obvious, maybe a bit more trivial. And I suppose my goal with this video is to give 3 examples of situations where statistics really isn't trivial and where we do have these really deep, profound questions about what statistics actually are, what odds actually are, and that it isn't actually also obvious. I will admit that I'm using the term paradox here quite liberally. When I say a paradox, I more mean something that feels paradoxical. The last 2 examples I'm going to give are going to be more like real paradoxes. The first one actually won't technically be a paradox in the sense that there is a correct answer, but the correct answer is quite unintuitive, so I'd like to still speak about it. This first example is a problem called the Monty Hall problem. This is a very famous problem. I wouldn't be surprised if a lot of the viewers have heard of it at some point. I'll quickly go over how it works. So you're on a game show and you've made it to the final round or something like that, and this is you, and there's a host. So this is you and this is the host, and we'll make the host a different color. We'll make the host red. All right, so behind one of these doors is a prize, something worth winning. I think most of the time the prize is a car. So behind one of them is a car, and behind the other 2 are prizes that aren't so desirable. I think the example is a goat. So we're gonna say there's a car and there's 2 goats. So 2 of those doors have a goat, one of them has a car. And you don't know which is in which door. You didn't see anyone sit the car in before the game started, so it's just a 1 in 3 chance for you. Now the way the game works is that you pick a door. Let's say, for example, you pick door 1. And then, and this happens every time, the host is then going to open up one of the 2 doors that you didn't pick to reveal a goat. Note that he can do this every time without fail because there's 2 doors that you didn't pick and there's only 1 car, at least one of them has a goat. So the host then opens up door 2. Door 2 has been opened. And inside is a goat. I can't draw a goat, so we're just going to give a thing with 4 legs. This is my goat. Alright. And then he asks you, would you like to switch your choice? Would you like to stop picking door 1 and again change to door 3? The question is, should you switch? Does it matter if you switch? Now, the most intuitive takeaway from this problem is it doesn't matter. And most people actually would say that they want to stay, because if it doesn't matter, why change? You know, I'm changing does nothing. People have an attachment to what they already picked, so they want to see it through. The idea here is that this is going to be 50% chance, and this is going to have a 50% chance. Now, this is wrong. Switching actually is beneficial. And the true answer to this problem is that your door has a 33% chance of having the car, and the other door has a 66% chance. This is like recurring. This is 0.66. This is 3.3333. And I'm now going to talk a little bit about why. The best way to explain why, I suppose, is because the host had to open up another door, and the host was always going to reveal a goat. So by him opening up the other door, which is something he was always able to do, you didn't get any more information. It didn't make your odds go up because nothing happened that wasn't always going to happen. It wouldn't make any sense if your odds went up to 50% here because you didn't earn it. There was no real thing that happened that would make your odds go up because what happened was always going to be able to happen. So one way that I like to think of it is that the odds that this door had a car in it have now sort of been transferred to door 3. I'm going to prove it properly as well, because again, this is quite unintuitive. So let's say that you've picked door 1, because again, it shouldn't matter what your opening pick is. You picked door 1, and I'm going to go through basically the 3 scenarios. So there's 3 scenarios for doors 1, 2, and 3. In scenario 1, the car is here, and the car can be a circle. Scenario 2, the car's here, and scenario 3, the car's here. And to make it fair in all three scenarios, you pick door 1. So in the first scenario, you pick door 1, and then the host is going to reveal a goat door. Now in this case, the host can pick either door, it doesn't matter. So let's just say he picks door 2. And then he asks, do you want to switch? And here, if you say yes and you switch, you lose. So here you didn't want to switch. Now in the second example, you pick door 1, and he has to reveal a goat door. So he has to reveal door 3. This is the only door he has that has a goat in it. And then he asks, do you want to switch? And if you switch, you win. Now in the third example, you pick door 1. He had to reveal door 2 because it was the only door with a goat in it that was available to him. And then he asked, do you want to switch? And if you switch, you win. So if you think about it as if these are the only 3 possibilities, and these possibilities are all equally likely, and in 2 out of the 3 possibilities, you won by switching, and the other one you lost. This is another intuition for where that 2 out of 3 odds come from. Another nice way to think about this is to just increase the number of doors. And the more doors you have, the more obvious it is. So let's say the doors are labeled 1, 2, 3, 4, blah, 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 blah. And let's say there are 1,000 doors in the game. And then you pick door 1. So you've picked door 1. And in this game, it seems like it's going to be very hard to win the car because there are 999 other doors the car can have. But then let's say the host then has to reveal 998 doors that had a goat in them, right? In the same way as the 3-door game. He's basically going to leave you with one other option. And let's say he opens up door 2, door 3, door 4, and all the doors besides door 1,000, except he happens to leave door 362. So now your options are, do you want to keep door 1? Or do you want to switch to door 362? And now I think the intuition is clearer because it feels a lot more suspicious that the host happened to leave this door open. It was almost as if he had to. You know, it's like, why did you open door 362? You could have not opened that door. Hopefully it's clear that this happening, because it always could have happened, didn't make your odds any better. Your odds are still 1 in 1,000. Because the host was always going to be able to find 668 doors with no goat. Which means that if you switch, your odds of winning this game are actually 999 over 1,000. Very high odds. If I did the same argument the second time and I considered all 1,000 possibilities, this is the result we would find as well. Alright, that's Monty Hall problem. And yeah, it's not really a paradox because there is a correct answer, but it is a very unintuitive one. Now I'm going to talk about something that's more akin to a paradox, and that is called the Sleeping Beauty problem. Sleeping Beauty problem. Here's how it works. And this is a hypothetical, it doesn't really matter why the hypothetical is happening. But let's say you're about to be put under a general anesthetic. You're basically going to be in a coma. You're not going to know anything while you're in this coma. So you're going to be in a coma. Let's just say, I don't really know how to draw this, but you're sleeping on the bed in the hospital or whatever, and you've dozed off. You don't know what's going on, right? You know that once you get put in the coma, the doctor or whatever, whoever put you in the coma, is going to flip a coin. He's either going to flip heads or tails. Now, if he flips heads, he's going to wake you up on Monday. Cool, simple enough. Let's say it's currently Saturday or Sunday, it doesn't matter. If it's heads, he's going to wake you up on Monday. If it's tails, he's going to wake you up on Monday. He's going to wipe your memory of being woken up on Monday, so you'll forget about it. You go back to sleep, and then he's going to wake you up on Tuesday. Now you know he's going to do all this. You know this is going to happen. The question is, you get woken up, and you get asked a very simple question. And he asks you, what are the odds I flipped heads. What is your answer? Now, interestingly, this is similar to the Monty Hall problem, and the debate is going to be 50-50, half chance, or 2-3. Or I should say 1-2, 1/3 chance. What are the odds I flip heads? Well, a coin flip is 50-50. We know that, right? This coin has two states, one is heads and one is tails. So an answer that might be a naive answer, but a really valid answer to this question is 50-50. Because those are the odds, 50% odds of head. But if you consider the fact that you were woken up, you can make the case, well, there's three ways that I can be woken up. I can either be woken up on Monday after heads has been flipped. I can wake up on Monday when tails has been flipped, or I can wake up on Tuesday when tails has been flipped. And out of the three ways you can be woken up, only 1/3 of them meant a head was flipped. And 2/3 of them meant a tail was flipped. So the other answer people give to this question is 33.3%. Now the interesting thing here is that this is more of a philosophical question about what it actually means to ask about the odds something happened. And my solution to this paradox is that I don't even think the question is posed fairly. I don't think it makes sense to speak of the odds that something already happened. I think philosophically we can say that the odds are either 100% or 0%, and you don't know. So I would actually say I don't know. I don't know what the odds are. Now obviously what they're asking you is what are the odds from your point of view, so I suppose we can try and engage with the question. I think there's a very strong case to be made that you're not allowed to use this argument with the 1/3 and the 2/3. And the reason is because you knew you were going to be woken up at least once and asked a question. So the fact that you were woken up shouldn't sway it at all, because it was always going to happen. In the same way that in that Monty Hall problem, you knew they were going to reveal a goat. So when they reveal a goat, it shouldn't have changed the odds. I'm torn on what the obvious answer to this question is, but I've been talking about it with a lot of friends. You can edit the problem a little bit by saying, let's say, heads, they wake up on Monday, tails, Monday, Tuesday, Wednesday, Thursday, Friday, they do it for 100 days. That's a nice way to really test the consistency of the 50% people, because they really need to still say 50% to be consistent here. But this person is going to change their answer to like 1% or something like that. But yeah, this is called the Sleeping Beauty problem. And I think it really ties into an interesting philosophical question about what odds actually are. Alright, and the final paradox I want to talk about is something called the Simpsons paradox. This one actually has the word paradox in the title. And it's not related to the Simpsons, unfortunately. So the Simpsons paradox. Now, I think that's fine. We'll capitalize it. Now this one I've saved an image to bring over because it involves a table. This one's really interesting. Alright, here we go. Now, the Simpsons paradox is about medical testing, or actually any sort of testing. But let's say we're testing a drug for how viable it is for the market, something like that. And these are our control groups. Group 1 was tested, 40 people were in group 1, and 22 of them, in 22 cases the drug was valid, or the thing passed, whatever, it doesn't matter. And then in group 2, 3/4 of them passed, so only 4 people, 55%. And so in total, 57% of tests passed. That's result A. This is one thing that could have happened. It's important to say these are both different drugs or different sets of tests. So let's just say this is like drug 1 testing and this is drug 2 testing. The question is that with the data in the table, what drug is better? I'll write that. What is the better drug? And it kind of seems obvious because in this total section, while we've seen that this drug is past 57% of cases, but this is past 68% of cases. Now, obviously, 57 is less than 68, and in both cases, there were exactly 44 tests. So, obviously, drug 2 should be better, right? It gets weird when you consider that in both individual sets of tests, drug 1 outperformed drug B, or drug A outperformed drug B, right? 55 is bigger than 50, and 75 is bigger than 70. So if, for example, instead of our groups, they were just days, so let's say these were all the Saturday tests, and these were all the Sunday tests. Well, what we can say is that even though drug B seems to be better overall, drug A was better on Saturday, and drug B was better. Drug A was better on Saturday, and drug A was better on Sunday. So why is drug B better overall? It shouldn't make any sense. The reason these numbers can behave this way is because obviously these fractions are different. So this one is a smaller fraction, this is a bigger fraction, and then they flip around. That's why these numbers can behave this way. And in some respect, this is an open question. And I think in the Saturday-Sunday example, the breakdown of Saturday and Sunday should be completely trivial. It shouldn't matter at all. So I would probably say that drug 2 was definitely better. But it does make me very uncomfortable that on both individual days, drug 1 was better. Now, what if I changed it from, instead of group 1 and group 2 being Saturday and Sunday, group 1 was tests on women, and group 2 was tests on men. Now we're dividing up in a different way. Now I feel like I'm more inclined to say that drug 1 was better, because it was better for women, and it was better for men. And that seems a lot more important than just being better on a Saturday and better on a Sunday, right? So even though drug B worked out better overall, I think that because women and men are different, and maybe they respond differently to the drugs, on average obviously, I'm more compelled by this separation of the data to say drug 1 was better. I'm going to draw a little chart now to sort of illustrate what's going on. What's really happening here is we have a table, and I'm just going to show the data. So let's say this is the effectiveness of something, and this is the oh, actually no, this won't matter. It'll be clear when I draw the things. It completely depends on what we're actually measuring, but I'm going to plot some data on this scale, and we're going to be analyzing the trend of the data. Basically, is this thing positive or is it negative? And let's say the data looks kind of like this. Cool. I think this is a good example. And what we're asking here is there an upwards trend or a downwards trend? And this is going to be asked a lot of the time in a lot of different settings, because we want to know if this variable here, which we'll call variable 1, has a positive impact on variable 2. You know, this is some diet and this is cancer rates. It doesn't really matter. Does variable 1 have a positive effect on variable 2? And if we consider our blue and red clusters as separate from each other, then the answer is very clearly no, because in group 1, the data went down, and in group 2, the data went down. So obviously variable 1 has a negative impact on variable 2. And that's basically the same as saying that, well, the drug is better for men and it's better for women, therefore it's better overall. Now another way that we could view this data is we could just say that the grouping is completely irrelevant. It doesn't matter that some of the dots are red and some of the dots are blue. They're all measuring the same drug or the same thing. So the overall trend is positive. And if you did like a mean square test on this data, this is what you might get. I'd have to maybe put in a few more dots here. But you can see this is actually the true pattern of the data, right? So interestingly, my result was completely opposite based on whether or not I'd considered this grouping to be valid or not. If this grouping was just like Saturday tests and Sunday tests, or if it was just completely arbitrary and random, I would tend to support this conclusion. Or should I say this conclusion? The one that says that the overall sum works more, that the thing is positive, right? Variable 1 has a positive impact on variable 2. But if this grouping seems more important, like men and women, or maybe testing for different age ranges, something like that, then I'm much more confident to say that, well, variable 1 has a negative impact on variable 2. Anyway, that's the Simpsons paradox, and the idea just basically says again that how you choose to group your data when you analyze things is very complicated, and that it matters. And it's not always obvious when you do a study what groups you can break things down by, because you can't break it down by every group, because everyone's going to have their own category, because everything is in at least one different group from everything else. So you've got to pick reasonable groups. And the question in statistics, which is a question I'm not going to get into, but the question that this poses is, what are reasonable designations for groups? Obviously Saturday and Sunday isn't reasonable, because it shouldn't matter, unless maybe it rained on Saturday or something and not on Sunday. But women versus men does matter, or under 35, over 35 matters. And that's the end of my 3 paradoxes. Thanks for watching, guys. Cheers.